The moon lifts itself over a horizon of slow-breathing waves. Along the pale curve of a tropical beach, something ancient is already stirring beneath the sand. The nest's top layer collapses inward, releasing a hush of dry grains. Then, like a hand unfolding in the dark, dozens of tiny heads push through. Hatchlings, smaller than a human palm, eyes already tuned to faint horizons, emerge into a world that has waited for them longer than any civilization. The sand still holds the warmth of the day, and above, the Milky Way sketches out the first map they will ever know. For each hatchling, this is not a simple dash for the sea. It's the single most critical orientation exercise of its life. The beach is full of cues: the cool moisture ahead, the downward slope of the sand, the shimmer of light reflected off the water's surface. But instinctively, they ignore everything that isn't ocean. The physics of their first few minutes determines who will live to see dawn. Their bodies, perfect in miniature, are built for this test. The front flippers act like wings, long, flat, and edged for thrust. The rear pair, smaller and paddle-shaped, serve as rudders to correct each wobble. The shell, still soft from the nest, is hydrodynamically curved even now, a teardrop profile shaped by millions of years of surf-crossing ancestry. When the first one breaks from the dune shadow, 100 more follow. It's not a random rush, but a collective surge timed to darkness. Cooler air means fewer ghost crabs, fewer gulls, fewer hawks awake to spot movement. The sand beneath them is alive with heat shimmer and vibration, each grain a hazard, each second an exposure. If the moonlight hits wet sand, it becomes their North Star. They sprint downhill in a zigzag pattern, a jitter of momentum that looks chaotic but aligns perfectly with wave reflection angles. The ocean's low-frequency thunder, that deep, continuous roar, becomes their first compass. Hatchlings that stray inland are lost to confusion or exhaustion within minutes. Then contact, the edge of the world. Foam swallows them, tugs backward, and here the real physics begins. The first wave they meet is their first teacher. It's not just a wall of water, it's a vector. Each breaker carries directionality, a dominant push that the hatchling's inner sensors record through vestibular feedback and pressure gradients across the body. As they paddle through the surf, they feel the angle of wave approach. Those who align their swimming toward the oncoming waves automatically move away from land. Those who don't spin back to shore and vanish. It's called wave compass orientation, a system built entirely on physics and nerve endings. Tiny mechanoreceptors in the inner ear detect tilt and acceleration, while stretch sensors along the neck and flipper joints relay feedback about motion through moving water. The turtle's brain converts those sensations into a simple binary truth. Toward the waves means toward safety. This rule will serve them for the next half hour, and for most, it's the difference between life and death. Beyond the breakers, the ocean's tone changes. The roar softens into pulse. The world below is infinite and without shape. Here the wave compass no longer helps. Now the second map unfolds, one etched not in sound or sight, but in the invisible pull of the planet itself. Every hatchling carries in its tissues a set of magnetite crystals, microscopic grains of iron oxide embedded in sensory neurons around the brain and nasal region. These act as biological compasses, aligning with Earth's magnetic field. As the hatchlings swim, they feel the tilt and intensity of those magnetic lines, which vary predictably across latitude and longitude. Through this sense, they construct a mental map, an imprint of their birthplace that they will use decades later to return. This magnet map isn't static. The turtles learn by experience. Ocean currents drag them across vast gyres, swirling systems of warm and cool water that act like conveyor belts. Those that hatch on the Atlantic side enter the North Atlantic gyre. In the Pacific, the equatorial countercurrent may carry them thousands of kilometers. Yet throughout these years of drifting, they remain oriented. When currents shift, they adjust headings subtly, recalibrating to maintain the geomagnetic signature that feels like home. Scientists have demonstrated this uncanny navigation in controlled tanks. Expose a turtle to a magnetic field replicating Florida, and it will swim east. Simulate the field near Africa, and it will turn west. The compass and map are one, a feedback loop between physics and instinct. But this system depends on one fragile thing: getting through those first 5 minutes. Artificial lights from coastal cities and resorts are now among the most potent disorienters of all. Hatchlings mistake the glow of street lamps for the ocean's reflected sky and head inland, crossing roads or drying out in the dunes. Others reach the water but find themselves caught in rip currents, their tiny flippers no match for lateral undertow. Each hatchling has only a limited energy reserve, stored as yolk residue within the belly, enough for a single night of swimming before starvation begins. If they fail to clear the surf zone, they don't get a second chance. Those who make it offshore begin the frenzy swim, a non-stop 24-hour drive away from land. In that time, their muscles operate near maximum efficiency. Unlike land reptiles, hatchlings maintain partial endothermic control during swimming, microbursts of muscular heat buffered by shell vascularity to prevent fatigue. It's an evolutionary bridge between cold-blooded metabolism and the demands of an oceanic life. By dawn, they're kilometers away, riding the soft rise and fall of swells that lead toward open current systems. Once they merge with those flows, they vanish into what researchers call the lost years. The turtles drift within floating sargassum mats, feeding on tiny crustaceans and hiding beneath yellow weed. Their shells darken, their flippers strengthen, and the magnetic map in their brain refines with every seasonal oscillation. The hatchling that once swam by wave angle alone now understands the magnetic rhythm of the world, the difference between subtropical calm and equatorial upwell, between morning sun and thermal layers that signal approaching continents. By adolescence, each has built a navigational database more precise than any satellite coordinate, and all of it based on two simple inputs: wave direction and geomagnetic field. This sensory system is a masterpiece of evolutionary engineering. The turtle doesn't think in maps, it feels in vectors. Magnetic cues aren't abstract. They manifest as comfort or unease, as a subtle sense of rightness when aligned with the correct heading. Even temperature gradients contribute. Ocean thermoclines can bend magnetic field lines slightly, creating layered roads of conductivity that correspond to specific migratory corridors. Adult turtles later use these same corridors to travel between feeding grounds and nesting beaches, separated by entire ocean basins. The females that once sprinted from a nest in Florida, Brazil, or Western Australia return decades later to that same stretch of sand, guided by the faint magnetic fingerprints stored since their first swim. Yet for all this precision, the system is vulnerable to change. Human-made magnetic interference, undersea cables, drilling equipment, and even large-scale coastal infrastructure can distort local fields. Shifts of just a few microteslas are enough to nudge migration lanes off course. Add to that the rising brightness of coastal light pollution, and the once reliable wave compass is dimmed. Hatchling survival rates in some regions have dropped to single digits. What was once a perfect two-phase navigation system, short-range wave queues and long-range magnetic lanes, is now an obstacle course of altered physics. Still, resilience defines this lineage. Sea turtles have been reading the planet since before continents held cities. Their ancestors swam with ichthyosaurs, nested before birds learned flight, and persisted through 5 mass extinctions. Each new generation repeats the same elemental ritual: find the sea, ride the field, return. Watching them cross the surf, you see more than instinct. You see an organism synchronized with the earth itself, tuned to its electromagnetic breath. As the last hatchling disappears beyond the foam, the beach quiets again. The sand covers the emptied nest, the wind smooths away their tracks, and the waves resume their ancient rhythm. Somewhere beneath that silver horizon, a pulse of magnetic memory locks into place, a coordinate encoded in flesh. When this turtle is grown, it will follow that pull back through currents, storms, and continents, arriving again on this same strand of sand. That's the unbroken rule of the sea turtle's design. Every journey begins in vibration, a wave's push, a planet's hum, and ends where both first met. The last of the sun bleeds out across the scrub. Shadows stretch long and soft over a mosaic of pale grass, ironbark roots, and spinifex mounds. The air is still, a kind of suspended quiet that only the Australian interior can hold before the night pulse begins. Out of that silence comes a rhythm, soft thuds, evenly spaced, elastic in tone. The first wallaby clears the ridge at a shallow angle, tail balancing like a counterweight. Then another follows, bounding low, each leap perfectly tuned to the contour of the land. The mob appears almost weightless, suspended between earth and gravity, each movement a negotiation between muscle, tendon, and terrain. Their world is a calculus of efficiency. Every motion must pay for itself. In this landscape, where food is patchy, water transient, and predators swift, survival depends not on strength, but on the physics of rebound. The wallaby's hind legs are masterpieces of biological engineering, twin levers powered not by brute muscle alone, but by a system of elastic tendons that store energy like compressed springs. As the animal lands, its body weight stretches these tendons, primarily the long Achilles and digital extensors, storing potential energy in collagen fibers. On the next jump, that energy releases, propelling the wallaby forward with minimal muscular effort. It's a closed-loop economy, energy borrowed from one stride repaid in the next. In slow motion, the biomechanics reveal something astonishing. The muscles of the thigh hardly change length during hopping. They act more like stabilizers than engines, holding tension constant while the tendons do the real work. Each landing loads the system with up to twice the wallaby's body weight, yet the structure rebounds effortlessly. This elastic recycling is so efficient that at moderate speeds, a wallaby's oxygen consumption barely increases, a physiological feat no quadruped can match. The faster they hop, the cheaper each meter becomes in terms of energy cost. For a predator like a dingo or wedge-tailed eagle, the equation is reversed. Longer chases cost exponentially more. Efficiency, not velocity, decides who wins. The land itself tests that principle. The grassland here isn't smooth. It's stitched with fallen logs, termite chimneys, and invisible dips that could swallow a careless foot. Wallabies adjust instinctively. Each hop is calculated microseconds in advance. Tail angle, takeoff slope, and flexion depth vary to maintain a constant energy return. The tail, often underestimated, is not just a balance tool. At slower speeds, it functions as a fifth limb. When grazing or moving deliberately through thick scrub, wallabies use a pentapedal gait, placing the tail like a crutch behind them to lever the body forward as the hind legs swing in unison. In these moments, the tail bears nearly a third of the body's weight, a muscular, jointed column of bone and tendon that anchors every controlled motion. As dusk deepens, the grasslands come alive. Crickets begin their pulse, and the scent of eucalyptus oil drifts low through the cooling air. Wallabies spread out, nibbling tender new shoots that sprouted after recent rain. Their digestive system, part of the macropod design, is slow, deliberate, and adapted to austerity. A complex forestomach ferments fibrous plant matter, extracting nutrients with microbial efficiency. It's a system that wastes nothing, mirroring the economy of their movement. In a world where each calorie may cost kilometers of travel, efficiency becomes a way of being. But the open plain also means exposure. Out past the shadows, a dingo stirs, patient, unhurried. Wallabies rarely see the predator before it's close. They feel it instead through vibrations transmitted by the ground or the subtle rise of alarm from nearby birds. The mob tightens. Then, as if signaled by some unspoken cue, they launch. What follows isn't a stampede, but a measured series of arcs, each one deliberate. They do not sprint blindly. They zigzag between low scrub patches, recalibrating on each landing. Their goal is not to outrun, but to outlast pursuit, to make every acceleration efficient enough to preserve energy for the next 100 meters. Predator evasion, in this sense, becomes a problem of mathematics. For the wallaby, the challenge is to maintain elastic rebound without overextending, to stay just fast enough that the dingo's linear sprint burns through fuel too quickly. Each hop has a ratio of cost to gain, too shallow, and drag from grass resistance slows progress. Too steep, and the vertical lift wastes energy. In controlled lab settings, biologists have found that wallabies spontaneously adjust hop height according to terrain resistance and visual clutter. It's a self-optimizing algorithm written into muscle memory. Over open ground, they adopt long, shallow arcs. In scrub corridors where obstacles rise suddenly, they switch to high, controlled jumps, landing softly before immediately reloading the tendons for the next burst. Every leap is feedback, a live calculation balancing muscle tension, tendon strain, and gravitational pull. To watch a wallaby in flight is to see tension transformed into grace. The back muscles ripple, the abdomen tightens, and the front limbs tuck inward to reduce drag. Upon landing, the tendons recoil silently, readying for another cycle. Even the fur contributes. Its fine texture reduces friction from air and vegetation, preserving precious microjoules of energy per leap. The system's perfection lies in its modularity. Whether escaping, foraging, or moving between waterholes, the same mechanics scale seamlessly to purpose. The animal doesn't need to think about conserving energy. It simply is conservation embodied. Yet this balance is increasingly tested by human-altered landscapes. Fencing fragments, ancient movement corridors, forcing wallabies to break rhythm or turn back. Each interruption costs energy, the equivalent of pulling the brake on a finely tuned spring. In dry seasons, when water sources shrink to isolated pools, these inefficiencies become lethal. Hopping long distances across cleared farmland, wallabies often face hard-packed ground that reflects rather than absorbs impact. The tendons, evolved for springy soil, now endure greater shock per stride. Over time, individuals adapt micro-behaviorally, selecting routes with more give underfoot, even if longer. Energy still dictates every choice, every risk. Their survival strategies extend beyond movement. Wallabies use thermoregulation behaviors that mirror their mechanical precision. During midday heat, they rest in shade or dig shallow depressions in cooler earth. Licking their forearms, a signature macropod behavior, coats the dense network of surface blood vessels with saliva, which evaporates to release heat. In drought conditions, this simple cooling mechanism can mean the difference between life and collapse. The tendons that give them power also conserve heat through limited blood flow, preventing internal temperatures from spiking during long-distance travel. It's a closed thermal and mechanical system, efficiency not only in energy but in endurance. As night fully settles, the dingo's chase fades. The wallabies regroup, their breathing steady, their silhouettes merging with the tall grass. One juvenile stays still longer than the rest, muscles quivering from exertion. Its tendons, though smaller and less conditioned, already follow the same laws: store, release, repeat. In evolutionary time, this system may have originated from the ancient tree kangaroos and their arboreal leaps. What began as a vertical propulsion aid transformed through open grass evolution into a horizontal efficiency engine. The land itself sculpted the lineage, trading height for distance, branches for plains. Every ecosystem shapes its residents into equations of survival. For wallabies, motion became mathematics, a formula of resilience written into tissue. They are living demonstrations of mechanical feedback. Tendons that think faster than nerves, limbs that recycle the force of their own fall. Even rest carries rhythm, the micro-twitch of muscle fibers repairing under moonlight, the quiet reset of springs before dawn. As first light breaks again over the horizon, the wallabies are already moving. Not running this time, but drifting, slow pentapedal steps through dew-covered grass. Their tails dig softly into the soil, levering them forward with the patience of animals who have long outlasted empires. When the heat returns, they will retreat to shadow, conserving energy for night. The cycle continues, compression and release, economy and escape. The system rule holds, energy recycling wins. In the long arithmetic of survival, it is not the strongest or fastest who endure, but those who waste the least between two heartbeats. The wallaby's grace isn't athletic, it's mechanical elegance refined by scarcity. In every hop across a dim plain, evolution whispers the same truth: the future belongs to the efficient. By mid-morning, the desert has begun to hum. Heat shimmers along the horizon where the dunes fold into flats of fine quartz sand. The air, though still, feels alive, vibrating with thermal tension as every grain begins to move microscopically in the wind's breath. From a distance, the surface looks empty, yet beneath it lies an entire hidden world, a stratum of burrowers, diggers and vanishers who treat the sand not as ground, but as water. Somewhere between these realms, a small pulse of movement stirs, the sand skink, an architect of disappearance. Barely the length of a finger, the skink's body glints like burnished bronze, catching light in microfacets along its scales. At this angle, it looks more liquid than reptile. The scales are not smooth. Under magnification, each is covered in microscopic ridges arranged like a herringbone. These ridges are not decoration, they are friction reducers. When the skink moves through sand, air becomes trapped between the ridges, forming a thin cushion that prevents individual grains from scraping too deeply into the skin. It's a living lubrication system, an evolutionary response to one of nature's most abrasive environments. The skink pauses at the base of a dune, head raised slightly, nostrils angled upward. Every breath samples the air for temperature and humidity, two invisible gradients that dictate when it can safely surface. In this ecosystem, sand is both habitat and hazard. The surface promises access to prey, beetles, termites, ant larvae, or a stranded grasshopper blown off course. But it also invites predators, kookaburras, goannas, and snakes, whose eyesight and thermal sensitivity make daylight a deadly equation. The skink knows the pattern: emerge only when the air is cool enough to prevent overheating, but warm enough that surface insects are active. For perhaps 30 minutes in the morning and another hour before dusk, the balance holds. When the skink moves, it does so with uncanny smoothness. Its limbs are reduced, the front pair almost vestigial, the hind pair acting more as rudders than supports. It pushes off with the side of its body in a wave motion, a traveling S that ripples from head to tail. The motion is identical to that of a swimming fish, except the medium is granular, not liquid. As the body undulates, the sand ahead of it fluidizes. Grains roll over each other, forming a temporary suspension that behaves like a dense fluid. The skink rides that fluid pocket, slipping through as if through water. Once it passes, the sand collapses back, leaving no tunnel or trace. It is swimming through Earth itself, unseen by any predator watching from above. This phenomenon, sand swimming, is one of the least intuitive forms of terrestrial locomotion. High-speed X-ray imaging has revealed that the skink's body never truly tunnels. It vibrates the sand, reducing friction so efficiently that forward thrust outpaces collapse. The physics here are extraordinary. Each wave of muscle contraction pushes sand laterally, generating lift, while the belly scales minimize drag. The result is forward propulsion at minimal cost. At its peak, the skink can dive into the substrate at a rate of several body lengths per second, disappearing completely within half a second. Above, a butcher bird lands on a branch, scanning. Its eyes can detect the faintest tremor on the sand's surface. The skink freezes mid-wave, half buried. Stillness becomes survival. Its body temperature climbs rapidly under the heat, but its physiology tolerates transient spikes. The blood vessels under the skin constrict, redirecting flow toward deeper tissues where temperatures remain stable. A few seconds later, the bird moves on, deceived by the seamless uniformity of the sand. The skink exhales, then vanishes fully, flicking its tail like a fin and letting the desert close over it. Below the surface, the light vanishes completely. The skink's world is now tactile and thermal. It sees in gradients, feeling vibrations through jawbones and temperature differences along its flanks. The upper sand layer can be 40 degrees Celsius hotter than the layer just 5 centimeters below. Here, in the cooler band, the skink rests. The sand muffles sound and buffers temperature. It also slows oxygen diffusion, so the skink lowers its metabolic rate, heart beating just fast enough to sustain minimal motion. The body becomes a quiet machine designed to wait. When danger fades, the skink resurfaces, breaking through with a shower of grains that cascade down its sides. Emerging is as controlled as submerging. Nostrils close off automatically to prevent inhaling sand, and the eyelids, transparent and overlapping, sweep like goggles to clear particles. The animal lifts its head, scanning for new movement. A darkling beetle stumbles nearby, antennae twitching. In a flicker, the skink lunges, jaws snapping with surprising strength. Prey and predator vanish together back under the surface, leaving only a brief depression that wind quickly smooths away. Predators, however, have evolved their own counters. Sand goannas, for instance, can detect the vibrations of moving skinks through the substrate, tracing the subtle pulse of granular displacement. When cornered, the skink's last defense activates: caudal autotomy, tail shedding. At the moment of capture, specialized fracture planes between vertebrae allow the tail to break cleanly. Muscles around the wound clamp shut, preventing major blood loss. The detached tail, still alive with residual nerve energy, writhes violently, thrashing against the sand like a live bait. The movement distracts the attacker for several seconds, often long enough for the skink to dive and escape deeper. Over weeks, a new tail grows back, shorter and stiffer, composed mostly of cartilage instead of bone. The cost is high, stored fat and pigment are lost, but in a landscape where every encounter can end fatally, regeneration is an acceptable price for survival. The relationship between the skink and its environment is one of constant negotiation. Temperature dictates everything, not just activity, but even perception. The animal's muscles generate very little heat. Instead, it must harvest warmth from external gradients. On cool mornings, it surfaces to bask near the base of spinifex clumps, angling its body to maximize sun absorption. The glossy dorsal scales act like miniature mirrors, reflecting infrared light downward into deeper tissue layers. Once internal temperature reaches an operational threshold, around 33 degrees, enzymatic activity peaks, digestion resumes, and reaction time accelerates. But linger too long, and the system collapses. Beyond 41 degrees C, cellular proteins begin to denature, forcing an emergency retreat below the sand. There, the temperature gradient reverses, cooler, darker, denser, a perfect refuge carved by physics. In this dynamic, the skink's survival rule is simple yet profound. Change the medium, reset the chase. Above the sand, it lives under the laws of sight and motion. Below, it moves by vibration and inertia. No predator can maintain both advantages. This dual existence defines the species as much as its morphology. To an observer, the skink is a flicker, a glint of movement followed by erasure. Yet each disappearance is a decision, a precise reading of thermal thresholds, predator probability, and oxygen trade-offs. This behavioral plasticity offers insight into a broader principle of desert ecology, adaptability through phase shifting. Many organisms here switch states, liquid to solid, surface to subsurface, diurnal to nocturnal, to manage extremes. The skink's body is effectively an amphibious vehicle for sand, bridging two environments that most animals must choose between. Even its coloration reflects this duality: pale gold on the back to mirror sunlight, darker bronze beneath to absorb warmth from the ground when needed. It's an evolutionary camouflage against both predator and entropy. By late afternoon, as wind patterns shift and shadows lengthen, the dunes begin to cool. The upper sand crust, once blistering, hardens under dropping temperature. The skink surfaces again, nose first, then head, emerging like a swimmer from surf. It pauses, half in, half out, testing the air. The first moths begin to rise, and in that dim light, it resumes hunting. Each movement now is a flicker of energy exchange, stored solar heat fueling one last burst of activity before night. The stars appear, and with them comes the desert's second temperature inversion, warmth draining upward, cold sinking fast. The skink feels it first through the belly, the sand cooling beneath. In response, it dives once more, submerging into the stable layer that will hold just enough warmth until dawn. Beneath a meter of fine grains, the desert quiets. Air pressure shifts subtly as the wind smooths over the surface, erasing the day's small dramas. The skink rests, body coiled like a compressed spring. Around it, other hidden life stirs. Antlion larvae, burrowing spiders, the slow descent of beetle pupae waiting for rain. The sand becomes its own ocean, a world with currents, boundaries and thermoclines, invisible to all but those who can feel its tides. Here the skink sleeps in the medium it has mastered. Above, the moon pours cold light over an empty plain. Below, life continues unseen, each breath a reminder that the line between air and sand is not a barrier, but a threshold. For the skink, every escape is a return to equilibrium, a calculated shift from one physics to another. In this hidden dance of mediums, survival is not about strength or speed, but transformation. The skink has learned what few animals ever master, that safety is not always where one runs to, but where one sinks beneath. Dawn spreads thin over the eucalyptus hills, painting long blue shadows across the slopes. The air carries a faint chill, a holdover from the night's cold. Beneath that stillness, somewhere underfoot, a faint grinding hum stirs, the sound of soil meeting purpose. A clump of dirt lifts, falls away, and from the dark mouth of a tunnel the wombat emerges. Its shape is unmistakable, low, broad, compact, an animal that looks carved directly from the terrain it inhabits. The eyes are small but steady, the fur a dusted charcoal brown that matches the loam around it. It sniffs the morning air, gauging humidity, temperature, and the scent trails of others. Then, with a slow sway of the head, it sets to work again. The wombat's world is one of angles and pressure, of torque, leverage, and weight transfer. Everything about its body is engineered for excavation. Its shoulders, anchored by oversized clavicles and dense musculature, act like a twin-piston engine, each forelimb capable of generating enormous downward force. The claws are thick, flattened and slightly curved, designed not for gripping, but for cutting through soil like blades. Even its skeleton tells a story of efficiency, the limbs set wide and low for balance, the spine reinforced to resist torsion. When it digs, its body hardly shifts. The motion happens from the shoulders down, a slow rotational drive that turns muscle energy into forward progress. Watching it excavate, one sees not a frantic scramble, but a patient machine, moving dirt as if turning gears beneath the earth. Each burrow is a blueprint of survival. Entrances begin on sloped ground, the soft embankments of creek beds, ridges or hill flanks, where drainage and soil composition create the ideal density for tunneling. Inside, the passage angles downward at roughly 30 degrees, leading into chambers that level out several meters below the surface. Some wombats dig alone, others inhabit networks of tunnels shared between individuals over generations. The soil temperature here remains stable year-round, a sanctuary from the violent swings of Australia's climate. On summer days when surface heat can exceed 40 degrees Celsius, the burrow holds at a steady 22. In winter, frost never reaches this far. For an animal with thick fur and slow metabolism, such constancy is a shield against extremes. The burrow's architecture is more than shelter, it's strategy. Each turn and narrowing is shaped with geometry in mind. The wombat's enemies, dingoes, feral dogs and wedge-tailed eagles, operate best in open ground. They rely on visibility and pursuit. But once the chase crosses the threshold of a burrow entrance, the advantage flips entirely. The wombat's low center of mass, which might appear clumsy above ground, becomes perfect alignment for underground acceleration. It can pivot sharply in the tunnel without losing traction, its short limbs generating bursts of power that no predator can match in tight quarters. If cornered within the burrow, the wombat deploys one of the most extraordinary defense mechanisms in the mammalian world, its armored rear. The rump is composed of thick cartilage and dense bone covered by tough skin, a built-in shield. When pursued, the animal dives headfirst into a tunnel, then stops abruptly, pressing its hindquarters against the tunnel roof and walls, sealing the passage with its body. The predator, now facing a dead end of impenetrable muscle and bone, has no leverage. If the attacker attempts to bite or claw through, the wombat can deliver a sudden backward thrust, a torque-driven shove capable of crushing a dog's skull or suffocating it against the burrow ceiling. It's an act of pure mechanical cunning, transforming vulnerability into architecture. The wombat doesn't outrun its pursuers, it outdesigns them. Brushfire season reveals the deeper genius of these subterranean fortresses. When flames sweep through dry eucalyptus forests, temperatures at ground level can soar beyond 600 degrees Celsius. Above ground, few creatures survive such intensity. Below, wombat tunnels remain untouched. The air inside circulates slowly through a network of side vents and collapsed roots, keeping oxygen levels adequate for hours. As the fire front approaches, wombats retreat underground, sealing themselves in the deepest chambers. Remarkably, during major bushfires, other species, echidnas, lizards, even small birds, have been observed taking refuge inside abandoned or occupied wombat burrows. Whether by instinct or coincidence, these animals recognize the tunnels as lifeboats carved by evolution's most stoic engineer. When the fire passes, the wombat re-emerges first, sniffing the ash-filled air, its fur unscorched, eyes squinting against the new landscape of blackened trunks. The wombat's digging does more than protect, it reshapes ecosystems. Each burrow acts as a hydrological valve. During heavy rains, water seeps through tunnel entrances and collects in subterranean pockets, recharging groundwater and preventing runoff erosion. Over decades, abandoned burrows collapse partially, creating microhabitats for invertebrates, reptiles, and small marsupials. Native grasses take root in the nutrient-rich soil piled at burrow mouths, stabilizing slopes that might otherwise wash away. Through nothing more than persistence and design, the wombat becomes an unwitting engineer of the landscape, a creature whose architecture sustains others long after its builders have moved on. Yet beneath this calm precision lies a constant negotiation with danger. Dingoes hunt at twilight when the wombat ventures out to graze. Its movements above ground are slow, deliberate, a shuffle that belies the explosive power beneath. Should a predator appear, the wombat bolts for the nearest burrow, legs pounding with astonishing acceleration for such a compact body. The tail, barely a stub, provides no steering, so the wombat's control comes entirely from shoulder torque and weight shift. In these moments, its gait transitions from lumbering to ballistic. A single downhill sprint may cover 100 meters in under 10 seconds. The goal isn't distance, it's access. Every chase is a race to geometry, the mouth of the tunnel where physics will once again take its side. Thermal stress poses another invisible threat. Unlike kangaroos or wallabies, wombats do not dissipate heat efficiently. Their dense musculature, optimized for force, traps warmth. Burrows become their thermoregulation chambers, the earth itself a coolant. They time their surface foraging to cooler hours, grazing on tough native grasses and sedges with rodent-like incisors that grow continuously throughout life. The chewing motion is horizontal, not vertical, like a pair of shears slicing through fibrous blades. This adaptation allows them to grind through vegetation that would blunt most herbivore teeth, a slow but efficient method suited to an animal with patience built into its biology. Inside the burrow, the air smells of soil, roots, and subtle musk. A mother rests in a side chamber, her pouch oriented backward, a trait shared only with other strong diggers like the marsupial mole. The backward pouch prevents soil from filling it as she excavates. Inside, a tiny joey clings to her teat, no larger than a mouse, hairless and pink against the dark. The tunnel around them vibrates faintly with the mother's breathing. The joey will not leave the pouch for nearly 6 months, and even then it will stay close to the burrow's safety until it learns the pattern of exits and escape turns by heart. For a species whose defense depends on architecture, knowledge of spatial geometry is learned early. Above ground, the night chorus builds. Frogs begin calling from the creek beds, and moths spiral toward the last glows of dusk. The wombat emerges again, this time to feed under starlight. Its movements are soundless, paws pressing softly into the damp soil. Each step is methodical, its head sweeping side to side to test scent and slope. To most observers, it appears solitary, but its presence leaves an unmistakable signature: cubic scat deposited at burrow entrances and atop rocks. The unique shape prevents the feces from rolling away, turning it into a territorial marker, a communication tool crafted through anatomical efficiency. The cubed form results from the intestine's variable elasticity, compressing fecal matter in distinct chambers. Even defecation, in a sense, reflects the same geometry that defines its burrow: precise, contained, functional. Occasionally, a wombat will pause mid-feeding and simply stand, sniffing the air. Its sense of smell is acute enough to detect predators hundreds of meters away, or to distinguish individuals by scent trail. If danger nears, the wombat doesn't panic. It pivots, lowers its head, and accelerates towards safety. The chase may be brutal and short, but the outcome is almost always the same. The wombat vanishes underground, the predator left at the entrance, panting and clawing at a wall of dirt that might as well be stone. The system rule is fulfilled again: escape into architecture. With dawn's return, the hillside quiets. Wisps of mist cling to the creek beds, and sunlight filters through charred gum trunks, finding its way into burrow mouths. Inside, the wombat sleeps, heart slowed, body cooled by earth. Above, life resumes its rhythm: birdsong, insects, wind through grass, unaware that beneath their feet the landscape is cross-hatched with unseen corridors, hundreds of meters long, carved by generations of marsupials that turned survival into engineering. The wombat's legacy is not speed or grace, but design, a reminder that strength can be measured in structure as much as motion. Each tunnel is a mathematical answer to every threat this land has posed: fire, drought, pursuit, heat. In a continent defined by extremes, the wombat has built permanence where others rely on flight. Its burrow is both shield and strategy, an act of torque and geometry that transforms the landscape itself into a fortress. In the end, the wombat's power lies not in confrontation, but conversion. The ability to turn the chase into stillness, the surface into shelter, and the physics of pursuit into the calm logic of a dead end. The sun has barely cleared the ridge, yet already the air trembles with heat. A shimmer forms above the rocks where sand meets stone, that flickering boundary where everything alive must master temperature before movement. From a shadowed gap between granite slabs, a shape uncoils, long, deliberate, scaled in the bronze grey of dusted iron. The goanna steps into view. Its tongue flicks once, twice, a forked ribbon of black sampling the currents. Scent is its language, heat its metric, the land a three-dimensional circuit waiting to be read. Goannas, the monitors of the Australian continent, move with the confidence of something built for endurance in a place that rewards precision over panic. Every motion begins in the spine. The head leads, the tail counterbalances, and the torso undulates laterally in a sinuous rhythm that couples directly with the stride of each limb. To watch one walk is to see torque translated into geometry, muscles in sequence, ribs pivoting, tail dragging like a metronome. With each step, the body's lateral swing amplifies stride length, allowing an animal over a meter long to cover surprising ground with minimal effort. It is motion by orchestration, not brute repetition. But the real brilliance of the goanna's design hides deeper, in its throat. Most reptiles face a biological contradiction. When they run, the side-to-side compression of the chest cavity restricts airflow to the lungs. Speed suffocates endurance. Goannas solved this with a trick of biomechanics, gula pumping. As it runs, the lizard rhythmically expands and contracts its throat muscles, drawing air in and out independently of the body's motion. This decoupling of respiration from stride means that a goanna can sprint for minutes where other lizards falter in seconds. The throat becomes a bellows, keeping oxygen supply constant even as the torso flexes like a piston. It's a built-in gear shift, a physiological innovation that turns a short dash into a sustainable chase. The scene around it vibrates with subtle life. Ants tracing invisible highways through spinifex roots, cicadas resonating from bark, the faint crackle of seeds splitting in the heat. The goanna's world is an archive of smells layered over time. Every flick of its tongue collects airborne molecules, delivering them to the Jacobson's organ in the roof of the mouth, where chemical cues are sorted into meaning. A fresh scent of carrion, a dusting of mammal hair, the faint musk of another monitor passing hours ago, all become coordinates in a moving map. The goanna travels not by sight, but by invisible trails that persist long after the source has gone. Its path leads along a dry creek bed littered with stone and bone. Here it slows, swinging its head side to side in deliberate arcs. Beneath one log, a burrow entrance breathes faintly cool air. The scent inside is rich with termite dust, a potential den site or hunting ground. The goanna pauses, testing. It knows this kind of mound, part fortress, part pantry. When food is scarce, it will raid these colonies, tearing through clay walls with claws built for leverage. But for now, the temperature is wrong. The sand here already reads close to 40 degrees, and body heat once gained is slow to lose. Every goanna moves according to a thermal budget, a balance sheet of sun and shadow. The day offers only narrow windows for full exertion. By late morning, the goanna shifts into its faster gear. Muscles tighten under the smooth scales, and suddenly the languid saunter becomes a glide. It accelerates across the open sand, each step a controlled explosion of power. The undulating spine transmits energy from shoulder to hip, tail swinging for momentum control. What looks effortless is deeply calculated. The coordination of over 100 muscles maintaining traction on unstable ground. As it runs, the gula pump works in visible pulses along the neck, keeping air moving through lungs that function more like those of birds than of reptiles. Partitioned, efficient, flow through. Oxygen feeds heat, and heat drives the chase. A sudden rustle breaks the rhythm. A young skink darts from the shadow of a grass tuft. The goanna pivots with astonishing agility, claws digging deep into the sand for traction. The chase lasts only seconds. When it ends, the skink has vanished into a root hollow, but the monitor doesn't seem disappointed. Hunting in this heat is as much reconnaissance as reward. Each pursuit sharpens the goanna's map of terrain, where holes lead, how obstacles shift, where scent paths converge. As noon approaches, the light hardens into white. The surface temperature spikes beyond tolerable limits. The goanna climbs a rock outcrop and halts, sides heaving slightly as it raises its head. Here, wind replaces shade. The stones act as both radiator and thermometer, their temperature gradient a code the reptile reads through its belly scales. When one section cools below its body's thermal optimum, around 35 degrees Celsius, it moves a few centimeters to balance heat gain and loss. This constant micro-adjustment is thermoregulation through geography, a reptilian calculus between metabolism and environment. Predators watch from higher ground. A wedge-tailed eagle circles, shadow sweeping the rock face. On open sand, there would be no escape. Speed is meaningless under talons that strike from above. But here, the goanna engages its third dimension, vertical. In an instant, it lunges toward a nearby tree. The claws, recurved, serrated, and designed for traction, bite into bark. The body elongates, tail pressing against the trunk for stability. Within seconds, it's 3 meters up, plastered flat against the bole, head turned skyward, invisible from below. The eagle passes, shadow flickering across the leaves, unaware it has lost its mark. This instinctive use of vertical escape is more than reaction. It's geometry as defense. The goanna knows, in the same way it knows heat or scent, that the shortest line between pursuit and survival is not horizontal. The z-axis is freedom. A predator adapted to flat pursuit cannot compute an instantaneous shift to vertical space. In that single motion, the goanna transforms a chase into a puzzle, the kind no dingo or bird of prey can solve without changing its own domain. From its vantage, the lizard rests, sides expanding in slow rhythm. Gula pumping continues, keeping oxygen circulating even in stillness. The world below rearranges itself, the shimmer of heat, the distant movement of wallabies among spinifex, the faint hiss of wind crossing the rocks. The goanna remains motionless for minutes, then resumes its climb higher, exploring the canopy. There, it finds a new dimension of opportunity. Bird nests hidden in hollows, eggs warmed perfectly by the ambient heat. Monitors are opportunists of the highest order. Their diet shifts fluidly between insects, carrion, eggs, small mammals, and even reptiles of their own kind. Each food source is another piece in the broader ecological engine, and the goanna's scavenging cleans the land of decay while feeding its relentless metabolism. Its physiology demands protein, and its predatory efficiency ensures that little goes to waste. The goanna's stomach acids are potent enough to dissolve bone and shell, turning every meal into pure fuel for movement. That metabolism, paired with exceptional heat tolerance, gives it the ability to sustain activity longer than almost any other reptile in its range. Yet even it must rest. By afternoon, When the ground radiates heat like a furnace, the goanna seeks shade beneath fallen timber, flattening its body to reduce surface exposure. The sand under the log is cooler by several degrees, and moisture clings faintly there. It closes its eyes, transparent eyelids drawn like screens, and slows its heart rate. In the reptile world, stillness is not inactivity, but recalibration. Evening brings transformation. The light softens to gold, the air loses its shimmer, and the land cools just enough to allow movement again. The goanna stirs, emerging from shadow. It begins its patrol anew, following scent lines it left earlier in the day, confirming what has changed. Near a dry burrow, a faint mammal musk draws its attention, perhaps a bandicoot or small rodent nesting inside. The goanna tests the entrance, claws scraping softly, then waits. Patience is its other gear, the one powered by strategy rather than muscle. Each night, this cycle repeats: movement, rest, observation, and recalibration. Across years, a single goanna may memorize the layout of dozens of termite mounds, hollow logs, and escape trees. It becomes an animate map of its territory, a living surveyor moving through a three-dimensional grid of possibilities. This mental cartography is what allows it to persist in landscapes that would defeat animals dependent on fixed routes. Fire can erase vegetation, floods can redraw creek lines, but the goanna's knowledge of structure, of elevation, refuge, and thermal logic persists. Its ecological role stretches far beyond its solitary hunts. By digging for eggs or carrion, it aerates soil and redistributes nutrients. Abandoned burrows become dens for snakes or nesting chambers for frogs during wet seasons. Scavenged carcasses are stripped clean, reducing bacterial load in the ecosystem. In every motion, climbing, running, burrowing, the goanna reshapes microhabitats for others. As darkness settles, the land exhales its stored heat. The rocks, now cooling rapidly, radiate warmth into the still air. The goanna moves one last time, positioning itself on a boulder that faces the fading light. It remains there motionless, silhouetted against the afterglow, the gular pouch rising and falling in slow rhythm. This is the reset, a final balancing of oxygen, temperature, and energy before night claims the desert. In the quiet that follows, the land seems to forget its motion. But the goanna never truly rests. Its body holds the memory of every sprint, every climb, every temperature curve. It has learned through muscle and instinct that survival in this environment is not about brute force, but about adaptability, knowing when to shift gears, when to turn the chase upward, and when to become part of the stone itself. Vertical is victory. In a continent of horizontal threats, of open plains, predators and sun, the goanna wrote its own rule. If the pursuit lives on one plane, survive on another. Through that single act of elevation, it broke the logic of the hunt and claimed a dimension all its own. The inland wind rises before sunrise, spilling over the escarpments and brushing through the dry paddocks. It carries the scent of crushed grass and distant dust, a steady current stretching from one horizon to the next. On its back rides a bird barely heavier than a paperback, wings broad and copper-bright against the pale sky. The Nankeen Kestrel appears to hang motionless above the earth, a living equation of air pressure and muscle control. To the untrained eye, it is floating. To physics, it is anything but still. Hovering in open air is not a gift, it's a negotiation. Every second, the kestrel remains fixed in space. It fights the drag and lift equations that normally drive birds forward. Unlike the hummingbird's high-frequency hover, which relies on rapid, symmetrical flapping, the Kestrels method is a feat of aerodynamics balanced on knife-edge precision. It uses the wind itself as a partner, adjusting its wing angles, tail spread, and head position to exploit tiny variations in airflow. When a headwind strikes its breast, the bird tilts ever so slightly, converting forward momentum into vertical lift. The wings beat not to climb but to hold. The tail fans out like a rudder, constantly flexing to fine-tune stability. From below, the Kestrel's motion looks serene. But high-speed footage reveals the truth. Every feather is in motion. The primaries twitch, each micro-adjustment countering turbulence that would topple a lesser bird. The eyes, wide, dark, steady, remain perfectly still. This is head stabilization, a neurological reflex that allows the kestrel to isolate its gaze from body movement. Even as the wings flicker and shift, the head holds level to the horizon, ensuring its field of vision remains unblurred. That steadiness turns chaotic air into a usable platform. The landscape beneath it is a patchwork of color and geometry, pale stubble fields, rocky verges, the dark veins of roadside drains. The kestrel reads this world differently than we do. Through ultraviolet sensitive vision, it perceives a hidden map, the glowing trails of rodent urine and scent markings invisible to human eyes. In sunlight, these lines form a spectral lattice across the ground, showing the daily commutes of mice and voles. The kestrel follows them from above, like flight paths on a radar screen. Each pulse of UV light reveals a recent trail, intensity fading with time. To hover is to read this living script without losing position. The hunt unfolds in silence. The kestrel's wings remain in motion, but the body stays centered in the air, a masterclass in controlled instability. It watches a field mouse move along one of its ultraviolet highways toward a tuft of grass. The wind shifts, a sudden gust from the east, and the kestrel reacts instantly, banking its tail to catch the new current, wings angling asymmetrically to maintain position. This adaptation is called gust foraging, turning the unpredictability of wind into a tool for aerial braking. Where falcons and hawks rely on stoops, long, fast dives that demand open space, the kestrel succeeds in cluttered terrain by refusing to fall. It converts air resistance into surveillance. A brief contraction of the flight muscles, and it drops 2 meters, still headlocked on the same patch of ground. The wings flare wide again, feathers splayed to double surface area. For a second it seems suspended by invisible strings. Then the moment breaks, wings fold, gravity reclaims the bird, and it falls. Not a dive, but a precision plunge. The kestrel strikes with talons forward, breaking a heartbeat before impact, using its tail as a spoiler to arrest descent. The mouse barely has time to twitch before it is lifted, limp, into the air. Atop a fence post, the kestrel settles, wind ruffling its cream and rufous feathers. It grips the prey delicately, head bobbing as it tears with a hooked beak. No wasted motion, no sound but the rustle of wings. The kill is small, the meal brief, yet this rhythm will repeat dozens of times before dusk. Every successful hunt hinges not on speed or brute power, but on control. The kestrel's relationship with wind is intimate, almost symbiotic. Where most birds fight turbulence, it exploits it. Each open landscape offers a new kind of energy terrain. Over flat paddocks, it uses constant headwinds for static hovering. Along cliff faces, it rides rising thermals. Over roads and embankments, it harnesses the updrafts created by moving air hitting uneven ground. These invisible structures of air are as real to the kestrel as rocks and trees are to us. It maps them daily, committing the patterns of morning breezes and evening gusts to memory. When conditions shift, when storms flatten the wind field or heat waves kill thermal lift, the bird changes tactics, trading hover time for glide and pounce hunting. Adaptation is its true predator's edge. The design of its body mirrors that adaptability. The wings are long but narrow, optimized for both endurance and precise control. The tail, proportionally oversized, acts as an adjustable spoiler. Its vertebrae are fused in key segments to resist torsion during high-torque maneuvers, while the shoulder joints allow subtle articulation for pitch correction mid-hover. The flight muscles make up nearly 1/5 of its body weight, yet the bone structure remains light enough for buoyancy in the faintest breeze. The kestrel's metabolism burns fast, but its engineering ensures every calorie of lift yields maximum observation time. This balance between energy and patience defines the kestrel's ecological niche. While larger raptors dominate thermals and sky lanes, the Nankeen kestrel thrives in the margins, road verges, open paddocks, quarry rims, and cliff faces where small thermals and wind eddies abound. These edge zones, shunned by heavier birds, form the kestrel's perfect arena. Farmers often see them hovering above the fields at dawn, perfectly stationary, while the grasses whip in the wind. Few realize that this apparent stillness hides a physics lesson, the art of stability in chaos. Predators of the kestrel, like crows or peregrines, struggle to pin down a hovering target. The same precision that keeps it steady in the air allows instant lateral bursts in any direction. With a tilt of its wings, the kestrel can translate hover into climb, slide, or dive, turning pursuit into confusion. Vertical mastery grants it escape routes that don't exist for ground hunters. When threatened, it doesn't flee horizontally. It simply rises, shifting into the Z-axis, where speed is irrelevant and control is king. The kestrel's daily schedule mirrors the thermal clock of the land. At dawn, when winds are soft but steady, it hunts intensively. By midday, rising heat creates unstable air columns, too turbulent for sustained hover, and it retreats to a perch, conserving energy through shade and stillness. Its feathers, rich in microbarbs, trap air for insulation against both heat and cold, while the pale underside reflects sunlight. During long waits, the kestrel gula flutters, vibrating the throat to release heat without panting, maintaining internal equilibrium even under the high sun. As evening cools the air again, the hover returns. In the amber light, the bird's plumage glows copper red, the signature hue that gives it its name, Nankeen, after the faded cotton cloth of early settlers. There is an elegance in its restraint. Unlike the falcon's thunderbolt stoop or the eagle's sweeping strike, the kestrel's power lies in its refusal to rush. Its weapon is steadiness, the ability to hold position until the world aligns beneath it. In physics, stability is often a measure of resistance to disturbance. In the kestrel, it becomes the very mechanism of predation. The gust that would dislodge another bird instead fuels its flight correction. The wind, unpredictable and restless, becomes an ally that keeps it aloft. On the cliff edge, with dusk gathering behind it, a kestrel hovers once more. Below, a band of voles moves along faint ultraviolet trails, the remnants of the day's feeding runs. The bird locks its gaze, tail flaring wide as the first cool gusts roll up from the valley. Each pulse of air lifts it slightly, feathers catching and flexing in precise rhythm. It rides the invisible topography of the wind with the ease of a creature born to read what others cannot see. Then, the pause, the drop, the soft impact. A single motion completes the circuit between air and earth. The kestrel rises again, prize in talons, silhouette framed against the dying light. Behind it, the sky smooths into indigo and the wind finally rests. The lesson of the kestrel is simple but profound. Motion without control is noise, and speed without stability is waste. In a world obsessed with velocity, this small raptor survives by mastering the pause. Hovering is not hesitation, it is precision extended through time. Steady equals deadly. The kestrel proves that in nature, as in physics, the true predator isn't the one who moves fastest, but the one who moves last, perfectly aligned, perfectly still, until the air itself becomes an instrument of aim.